We're going to talk first about symbology and the way in which we're going to do some diagrams. The start of this needs to be that when we do free body diagrams at the very beginning of the year and we first start getting into Newton's law, our free body diagrams tell us to take whatever our situation is and reduce it to a point. And then from there, identify the forces that act on the object. You know, we don't really know what the situation is, it doesn't matter. A free body diagram ignores the shape of the object. But torque, by definition, has to take into account the shape of the object because it takes into account the point of application of the force, right? We are measuring where the force is applied to the larger scale of the object. Net force never did that. Net force didn't care where the force was applied. So if you're dealing with say you have a floor here, we have a box, and you're told to apply a force to this box to slide it to the edge of this platform. You wouldn't care where that force was applied. You could be pulling on the box like this, or you could be pushing on the box over here, or you could push on the box here. It doesn't matter. You maybe pull on the box over here. We wouldn't have cared. We would have reduced the box to a point and dealt with the force from there. But anybody who's ever actually had to do work, meaning you have a job and your job was to move a box across the floor, understands that these are three very different ways to move this box. And that some of these ways could be catastrophic if the box were more like a bookcase full of something that couldn't easily tip over. You would understand that where you apply this force matters. And that's because if you apply the force here, that's a much different torque than if you apply the force here or here. And there's not an obvious pivot point. We don't know where the system might pivot. And we also know that since we're talking about moving the box, where the center of mass is probably likely to play a role in whether the system stays stable on its route over or falls over. All of those matter. So we're going to start with a more simplified idea. And I want to go back to talking about the door for just a minute, just so we have some symbology. When I say we're going to talk about calculating torque, there's two things about torque that you already know. One of them is that it involves what's called the torque arm, and that this is a cross product. That's what we started talking about when we were talking about the door. Today we want to get more into the nuts and bolts of it. So I want to remind you that you can write the phrase or the idea of the magnitude of the torque. This is magnitude simply by putting what look like absolute value bars on both sides of a vector. Say that I'm trying to find the size of the torque and not its direction. So the size of a torque involves three different and distinct measurements: the torque arm, the size of the force, and the angle between the torque arm and the force. We didn't talk very much about that part in our discussion about the door, but it should be clear that the most effective force is the one that is perpendicular to the door. If I want to get out of the room and I walk up to the door handle, I probably will be less effective at opening the door should I pull on the handle this way. Right? Grab the door handle and pull towards the hinge. Probably not particularly effective. People do it. People also tend to grab onto that handle and push straight down on the door handle. Not effective. Some of you have recognized that the most effective way to exit the room is to apply that force perpendicular to the door. That's why in our cross product, sine is a function that's used here. The sine of the angle represents a way of recognizing when your two forces are perpendicular to each other. All right, sine is a maximum at 90 degrees and is minimum at 0 or 180. So torques are more effective when the force is perpendicular to the torque arm. I don't want to say that 10 times. You should write it down though, because I know some of you have some weak trig out there. So if your trig is weak, force is most effective when the force is applied perpendicular to the torque arm. So let's handle some symbology first. Vocabulary, fulcrum, although a very popular science fiction name. Fulcrum represents pivot point. Pivot point. So the pivot point, or the point of rotation for your object. There's a lot of ways they'll say this on the AP exam. It all refers to the word fulcrum. Fulcrum, pivot point, point of rotation, those are all the same word. On a diagram, and you're going to have to learn to draw torque diagrams. Torque diagrams reduce your object's extension to how the forces are applied to the object. There is no specific rules for a torque diagram, at least none that I'm going to give you. Unlike a free body diagram, there are very few times in which you're asked to draw a torque diagram on the exam. Basically, a torque diagram usually is a two-dimensional picture of the forces acting on your object. All you have to be aware of is that you are responsible for figuring out where your pivot point is and be able to draw in the forces as they act on the object. So if this is our door, and let's say that we are above the door looking straight down, the fulcrum would be located at one end of the door. Fulcrum is drawn as just a small triangle, sometimes called a caret, that indicates where the system can pivot. If the force is being applied to the door, say here, oops, not there, say here, the torque arm is a vector that starts at the pivot point and is directed to the point of application of the force. I'll say that again because some of you should write things down. The torque arm is measured from the fulcrum to the point of application of the force. The torque arm has direction, so its origin is the pivot point, and the arrow side points at the point of application of the force. So this yellow arrow would be the torque arm. The force, in this case, is the direction that the push is coming from. Drawing the force where I have it there, or, hold on. Or drawing it here would be the same. Do everybody understand what I just did? Okay, so I'm going to keep it here because that's what I want to do. Because when you push on something, you tend to be standing on this side of it. But this and this picture are identical. The angle, we use traditionally the Greek letter phi for this, represents this angle or this angle. They're the same. Because sine is positive in both the first and second quadrant, it doesn't matter which of these two angles you use. Usually you use the acute angle. Usually. You don't have to. Mathematically, they'll be identical. So if you wish to use the obtuse angle, feel free. So I think it's very clear the direction of the rotation of the door based on this diagram. I always believe that any student looking at this diagram should have no trouble drawing in an arrow telling me which direction the door rotates. But I've been fooled by that, and that some people have a difficult time telling me the direction this rotates. When I look at it, to me, it's clearly rotating in this direction. But I've found that students don't necessarily see it that way. Now, the right-hand rule tells us which direction this rotates to. And we can use the right-hand rule to determine this direction. So I want to show. So based on using the right-hand rule, I would draw in that the torque is into the board. The circle with an X represents a vector that is into the board. A circle with a dot is out of the board. This symbology is supposed to represent an arrow that's either being shot towards you or an arrow that's being shot away from you. If the arrow shot towards you, you would see the point of the arrow that's out of the board. If the arrow is shot away from you, you're seeing the fletching, the feathers of the arrow. That would be into the board. All right? Everybody got all those pieces there? We'll see. In trying to figure out whether these torques are positive or negative, I want you to know that acceptable practice is out of the page or out of the board or out of the screen is generally considered positive, just as to the right is generally considered positive for X and up is considered positive for Y. Out of the page is generally considered positive for the Z direction. Now, before we get all busy on this, if you see one of these anywhere on your problem, they are telling you at the start of the problem all three positive directions. So if you have a coordinate system on your paper, they're telling you. Now, you guys know me pretty well at this point. You understand that I believe in choosing direction situationally, meaning you identify the directions that you're going to call positive at the start of your problem and be consistent. I will continue to maintain that is the best way to do these problems. That makes you mindful of direction. However, the book has a method for dealing with direction. Its method always makes out of the page positive, always makes to the right positive, and always makes up positive. Their method has less thoughtfulness about it and more repetitiveness about it. But after failing to do so correctly in sixth period, I'm not going into it. If you want to study their method, check out a book and read it. Otherwise, I'm teaching you the right-hand rule. So let's go through each of these. You take a moment and identify whether they're positive or negative by establishing that out of the board is positive. I'll wait 60 seconds. Let's take a look at them, see if you got them right. Torque 1 is negative. Torque 2, positive. Torque 3, negative. I'm going to skip torque 4. Torque 5 is positive. Now, I hope you guys got all those. I believe just by looking at them, you can easily see that this must be making this go this way. This must be making this one go this way. This one must be trying to make it go that way. This one must be trying to make it go that way. But of course, I want you to get the right-hand rule to work, and they could get more complicated than this. So let's talk for just a minute about how the right-hand rule would be applied to these, and then we'll talk about number 4. So if we're dealing with a two-dimensional object, we want to determine the direction of the torque. Now, I think just by looking at these, we should probably figure out whether it's causing it to go clockwise or counterclockwise, but perhaps not. Technically, to do it right, draw in your torque arm. Each one of these has a point of application of the force, and therefore there is a torque arm that can be drawn from the pivot point to where that force is applied. So I see that there should be 6 such torque arms. Now, with those torque arms in place, can you use the right-hand rule to identify whether these are out of the board or into the board? Again, we're stating that out of the board is going to be our positive direction. I'll give you a second. This is where the book's method does not work well. No, try. What?
About the last door.
We've moved on.
Okay.
Come on, Zach. I gave a clear opportunity here. I want you to try this. I want to finish this before the bell rings. Let's make sure we're using our right hand. And there's no reason not to spin the paper around when you do this. Otherwise, you look like a kind of a difficult person contorting to try and make it work. No reason for that. You'll just look silly if you get the answers wrong. So, given some pause, but torque 1, positive. Torque 2, positive. Torque 3, negative. There is no torque 4. Torque 5 is negative. Torque 6, positive. Are there any of these you'd like me to explain? Since the bell's going to ring now, please understand something important here. There is a mathematical anomaly in all of this. If you think back to your geometry, I know that's a lot to ask. The torque arm and the force are both rays. Remember what a ray is? Has a starting point and an arrow pointing away from it. No matter how those two rays are drawn, the two rays must define a plane in order for there to be a torque. And the torque is perpendicular to the plane. So in all cases, a plane must be defined. All of these, the plane was defined as the board, right? Because all of them had to be. In the way they were drawn, it's two-dimensional. But all cross products define a plane with the first two vectors, and your third vector is perpendicular to that plane. All right.